transformer. So transformer is the main reason why we go for per units analysis. Now we will see how we model transformer in per unit system. How we model transformer in a per unit system. So let us consider a single phase representation of a three-phase transformer as shown in the figure. Let us consider how do we represent the transformer. We have yesterday discussed that we neglect the magnetizing circuit. Okay. This is the load ZL. This voltage is V2. This is Z2. This is Z1. This is V1. I1. I2. This is E2. E1. Turns ratio is 1:8. So this is the single phase representation of a three-phase transformer. Okay, where V1, I1, Z1, E1 are the primary side values. Similarly, E2, Z2, I2, and V2 are the secondary side parameters. Okay, so the main idea in the conversion is the what is the transformer has two different voltages, two different currents, but it has only one single volt ampere specification. That is, the product of the volt amperes, that is the product of voltage and current on the primary side, is equals to product of voltage and current on the secondary side. So that's why for modeling of transformer, the common base MVA, let us call SB, is the common base MVA, common volt amperes or MVA, because we mainly deal with bigger machines. So repeatedly we call MVA. Otherwise you can write it as volt amperes. So common base MVA. Okay. Now let VB1, IB1 and ZB1 be the base voltage, base current and base impedance on primary side. Similarly, let VB2, IB2 and ZB2 be the base values on the secondary side. Understood? Why we don't have two different MVA, common base MVAs? Why? Because the machine rating is same either from primary or from secondary. So machine will have common base MVA rating, whereas the other base values will be different on both primary and secondary sets. Okay. Now the main point in reducing the transformer into per unit is we have to choose the base voltages. We have to choose the base voltages on either side of transformer, in the same ratio as voltage transformation ratio. That is, the point is we have to choose the base voltages on either side of transformer in the same ratio as turns ratio. That is 1:A. That is E1 divided by E2. That is the main idea. Okay, so that is the main point in resolving the transformer into per unit system, that we have to choose the base voltages on either side of transformer in the same ratio as the voltage transformation ratio or turns ratio. Understand? Similarly, you have ZB2 is equals to VB2 divided by IB2. VB2 divided by IB2. Okay. Now ZB1 by ZB2, that will be equal to VB1 by VB2 into IB2 divided by IB1. Okay. So this value, how you can write it as? This value you can write it as V1 by VB2 is 1/A, and similarly IB2 by IB1 is also 1/A. So this will become 1 by A square, which implies ZB1 into A square is equals to ZB2. Remember this relationship. Okay, that is the first relationship. Now, if you ask, sir, why this IB2 by IB1 is A, since the machine has the common MVA rating, so if you compute the product of, that is 3 times VB1 IB1, here we are choosing VB1 as the phase to neutral base voltage and IB1 is the base current. Okay, so since it is a 3-phase transformer, so the total MVA rating will become 3 times voltage into current. So the common MVA rating will become 3 times VB1 IB1 is equals to 3 times VB2 IB2, that is equals to common MVA base of the transformer. So from this relationship, what you can observe, 3 cancel. So VB1 into IB1 is equals to VB2 into IB2, which implies VB1 by VB2 will become IB2 by IB1, which is same as 1 by A. So that is why I am writing IB2 by IB1 as 1 by A. So the total product will become 1 by A square. Okay. From this figure, how do you compute V2 value? V2 is equals to E2 minus I2 into Z2. Okay. So V2, the voltage across the load V2 is given by E2 minus what is the current flowing through Z2 I2. So I can write V2 is equals to, let me change the ink, E2 minus I2 Z2. Okay. Now, how I can write E2 in terms of E1? So V2 will become, so if you remember this relationship, I want to write E2 in terms of E1. So it will become, E2 will become, from this relationship, E2 will become A into E1. So I'm writing it as A into E1 minus I2 Z2. Similarly, E1 I can write it as V1 minus input voltage minus I1 into Z1. So this is the V2. E1 is equals to, from this figure you can compute, E1 is equals to V1 minus I1 Z1. Okay. So now if I write every value, because all these are actual values, so from the definition of per unit, how I can write? Per unit value is equals to actual value divided by base value. So from this, what you are going to get? Actual value is equals to product of per unit value into base value. Actual value is equals to product of per unit value into base value. So now in this expression, I will write every term as the product of base value into per unit value. So V2 actual will become V2 base into V2 per unit. Similarly, A into V1, I am writing it as V1 base into V1 per unit minus I1 base into I1 per unit, Z1 base into Z1 per unit minus I2 base into I2 per unit, Z2 base into Z2 per unit. So I have written every value as the product of per unit value and base value. Now if I divide both LHS right hand side and left hand side with respect to V2 base, so I am dividing with respect to V2 base. So what I am going to get? Now here V2 base cancel. A into V1 base. A into V1 base is V2 base. So this V1 A into V1 base V2 base cancel. I1 base into Z1 base is V1 base V1 base into again A, it will become V2 base. So this is also cancelled. Similarly, I2 base into Z2 base is V2 base. V2 base are cancelled. So this A is also cancelled in both the terms. So what is left out? V2 per unit is equals to V1 per unit minus I1 per unit into Z1 per unit minus I2 per unit into Z2 per unit. So every value came in terms of per unit. Okay, V2 per unit equal to V1 per unit minus I1 per unit into Z1 per unit minus I2 per unit into Z2 per unit. Okay, this is the second relationship. Now, I1 per unit I can write it as actual I1 value divided by I1 base. Okay. Similarly, I2 per unit I can write it as actual I2 value divided by I2 base. So if you divide one with other, that is I1 per unit by I2 per unit, you're going to get I1 per unit divided by I2 per unit is equals to I1 by I2 into I2 base divided by I1 base. Okay. Now, if you consider an ideal transformer, if you consider an ideal transformer where V2 by V1 is equals to I1 by I2 is equals to, how you can write A. In an ideal transformer, V2 by V1 is equals to I1 by I2 is equals to A. So if you apply the same concept here, I1 by I2 will become how much? A, and I2 base by I1 base will become 1 by A. So this value is equals to 1. This value equals to 1. So which implies in a transformer, I1 per unit is equals to I2 per unit. That is, let us call the common value as I per unit. So the per unit current of the transformer is same on both primary side and the secondary side. That is the third important relationship. So per unit value of current on HT side and LT side is same in case of a ideal transformer. So I1 per unit, I2 per unit, I am calling it as I per unit. So if I substitute this in this equation, what I am going to get? V2 per unit is equals to V1 per unit minus, since both currents are same, I per unit into Z1 per unit plus Z2 per unit. Okay, so you can write this one in per unit representation of transformer. You can write this is V1 per unit, this is I per unit, this is Z1 per unit plus this is the per unit representation of the transformer. This is the per unit representation of the transformer in any phase. Okay, so here simply it is resolved into a series element. It is resolved into a series element. Okay, per unit representation of transformer. Okay, now if we further do the analysis, what is Z1 equivalent? The equivalent impedance of transformer with respect to primary. This I can write it as Z1 plus Z2 divided by A square, which you know. Okay, so if I calculate the per unit value of this one, that is Z1 equivalent per unit value, this will become Z1 equivalent divided by Z1 base. So if I calculate this, Z1 divided by Z1 base plus Z2 divided by A square into Z2 divided by A square into Z2 base. Okay, so this will become Z1 per unit plus, if you remember, A square into Z2 base, A square into Z2 base will become Z1. Sorry, this is Z1 base. I'm sorry. A square into Z1 base is Z2 base. So this will become Z2 per unit. So if you recollect this one, A square into Z1 base. So don't get confused. Somewhere I am writing ZB1, Z1B both are same. So A square into Z1 base is Z2 base. So which will give you what? Which will give you A square into Z1 base is Z2 base. Z2 base is Z2 per unit. So if you calculate the per unit value of the equivalent impedance on primary side, you are going to get Z1 per unit plus Z2 per unit. Similarly, if I calculate Z2 equivalent, what is the Z2 equivalent value? Z2 equivalent value, if someone remembers, A square into Z1 plus Z2. So if I calculate this per unit value, Z2 equivalent per unit is equals to Z2 equivalent divided by Z2 base. Because it is on secondary side, we have to use the secondary side base value. That is A square Z1 divided by Z2 base plus Z2 divided by Z2 base. So this value I can write it as Z1 divided by Z2 base by A square plus Z2 per unit. Because Z2 divided by Z2 base is Z2 per unit. Now similarly, A square Z1 base is Z2 base. Z2 base by A square will become Z1 base. So this value will become Z1 per unit plus Z2 per unit. So both Z1 equivalent per unit, Z2 equivalent per unit, both values are equal to Z1 per unit plus Z2 per unit. So that's why this value is nothing but the equivalent impedance per unit value, equivalent impedance per unit value. That either you calculate Z1 equivalent per unit or Z2 equivalent per unit, both values are same. So here, instead of writing both, you can simply write Z equivalent per unit. Z equivalent per unit. Understand? So that's why in transformer only the equivalent impedance referred to either HV side or LV side is given, because that is good enough to calculate the per unit value of the transformer. Okay, next. The last point, Z2 per unit is equals to Z2 divided by Z2 base. Okay, this value I can write it as Z2 divided by V2 base divided by I2 base. I am writing the denominator value into numerator. That I am writing Z2 base as V2 base divided by I2 base. Okay. Now for the same value, I am multiplying and dividing with I1 base and multiplying and dividing with V1 base. There won't be any change because I am multiplying and dividing with the same value. Okay. So Z2 per unit will become, if you recollect this one, what is I2 base divided by I1 base? And similarly V1 base divided by V2 base. What will be this value? So this will become Z2 into I2 base by I1 base. I2 base by I1 base is A. So ZT into 1 by A. Again V1 base by V2 base is again 1 by A. And what is the left out term? Left out terms are I1 base divided by V1 base. That is I1 base divided by V1 base. So this will become Z2 divided by A square into I1 base by V1 base. I am writing it as 1 by Z1 base. 1 by Z. In an ideal transformer, Z2 by A square, I can write it as Z1. So Z1 divided by Z1 base will become Z1 per unit. So Z2 per unit in a transformer is equals to Z1 per unit. So in an ideal transformer, so what are the conclusions we got? The conclusions we got are, if you draw up the transformer, in the transformer, your V1, I1, V2, I2, Z2 be the different values. Okay. V1 is not equals to V2. Similarly, V1 per unit is not equals to V2 per unit. There is some difference. I1 is not equals to I2, but I1 per unit is equals to I2 per unit. Z1 is not equals to Z2, but Z1 per unit is equals to Z2 per unit. Z1 equivalent is not equal to Z2 equivalent, but Z1 equivalent per unit is equals to Z2 equivalent per unit, and this value is equals to Z1 per unit plus Z2 per unit. You only have to remember these relationships. You only have to remember these relationships in a transformer. So in a transformer, the actual voltages on primary and secondary are different. That is, V1 is different from V2. Okay. And similarly, the per unit values are also different. In actual transformer, the primary current and secondary current are different, but in per unit system, both the currents are same. In actual transformer, the primary leakage impedance and secondary leakage impedance are different, but in per unit value, both are same. In actual transformer, the equivalent impedance referred to primary and the equivalent impedance referred to secondary are different, but in per unit, both are same, and whose value is equals to sum of Z1 per unit plus Z2 per unit. Only remember these four relationships. That is good. So what is given? Data is given. There is a transformer. The MVA rating of transformer is 250 MVA. The primary voltage or low voltage side is 11 kV, high voltage side is 400 kV. Okay. So the transformer has a leakage reactance per unit of 0.05 per unit on a base of 250 MVA. The primary and the primary voltage 11 kV. Then the actual impedance of transformer referred to the secondary side. The actual impedance of the transformer referred to the secondary side. So what he is telling, Z1 per unit, that is primary side leakage reactance of the transformer is J0.05 per unit. Okay. Now he wants you to calculate the actual leakage reactance of the transformer referred to the secondary. That means he wants to find out Z2 actual. Z2 actual. Very simple question. First logic is Z1 per unit in a transformer is same as Z2 per unit. So even the secondary per unit impedance is also J0.05. Now you simply have to calculate the actual value. So Z2 actual will become Z2 per unit into Z2 base. Okay. So Z2 per unit is given by J0.05. So what is the formula for Z base? It is V base square divided by S base. Okay. Since we are computing the base impedance on secondary side, so you have to substitute that values VB2 by SB2. VB2 by SB2. So it will become J0.05. What is the base voltage on secondary side? It is 400 kV. 400 whole square into, since the transformer has same MVA rating, so we have to choose SB as 250. So this would be the answer. So what is the option? 32 ohm. J32 ohm. Since it is a reactance, J32 ohm. Z2 actual. So any doubt in this question? It's simply testing whether you know the per unit impedance on the primary and secondary are same or not. Okay. So he has given Z1 per unit. So Z1 per unit equal to Z2 per unit. From there we have computed the Z2 actually. So one simple thing you have to remember in a transformer, whenever you are calculating the base impedance value, you have to choose the base voltage and base MVA referred to that particular side. Understand? So try to do this problem now. What is telling? It is a 4 kVA transformer with voltage of 400 and 200 volts. Okay, so he gave Z equivalent per unit, whose value is 0.02 plus J 0.06 per unit. Now he wants you to calculate the actual resistance and reactance referred to HV side. So that means Z equivalent referred to HV side will become Z equivalent per unit into the Z base on HV side. So this value will be 0.02 plus J 0.06 into what is the base value on HV side? It is V base HV whole square divided by S base. S base is common for both sides. So this will become 0.02 plus J 0.06 into HV side is 400 square divided by the machine volt ampere rating is 4000. So if you do this one, you are going to get the value as how much? Option B would be the right option. Option B would be the right option. Understand? Okay. Next. The next topic in our discussion is how to convert a single line diagram into per unit impedance diagram. So the first step in this one is, for entire power system network, choose a common base MVA. Okay. Next, choose an appropriate base voltage in one of the sections of power system network and calculate the base voltage in remaining sections of power system by using transformer line to line voltage ratio. Very, very important point. So the power system network will have only one base MVA, but it will have different base voltages and different base currents. So in one of the sections of power system, choose an appropriate base voltage and calculate the base voltage in remaining sections by using voltage transformation ratio of the transformers. Next, the third step is compute the per unit impedances of all the elements by using above base values and connect all the per unit impedances, same as single line diagram. Connect all per unit impedances same as the single line diagram. So these are the 4 steps to convert a single line diagram into per unit impedance diagram. Let me take a simple power system network to explain what is the section of power system. Randomly I am drawing. It is a generator, then there is a transformer, then there is a transmission line, and then there is one more transformer, and then there is a load. Okay. Now if you see this first transformer value is 11 kV bar 66 kV, let us say. The second transformer is 66 kV bar 6.6 kV. Okay. Now if you see this one, how many sections are there? The first section is 11 kV section. So this section is one section where your voltage is 11 kV. Okay. Next, this is one more section where your voltage is 66 kV. Okay, and there is a third section where the voltage is 6.6 kV. Okay, so this is a section where your voltage, base voltage, will be 11 kV. Here voltage is 66 kV. Here voltage is 6.6 kV. Okay, so these are the three different sections of the given power system network. Every section will have different base voltage and base current, but the base MVA will be common. Base MVA will be common. For example, if we assume that for this power system network, base MVA is say 100 MVA, and base voltage in transmission line, in the question they have given it as 66 kV. Okay, so the base MVA for this problem is 100 MVA. Base voltage in the transformer is given as 66 kV. Since there are three sections, I am writing the transformer section as section 2, whose base voltage is VB2. Now you have to calculate the base voltage of the 11 kV section or this first section by using this transformation ratio. What is the fundamental idea with which we developed the per unit representation of transformer? The base voltages on either side of transformer should be in the same ratio of the voltage transformation ratio. So VB1 by VB2 must be in the ratio of 11/66, because this is the voltage ratio of the transformer. So from this, which implies, already you know VB2 value, VB1 divided by 66 will become 11/66, which implies your VB1 is 11 kV. So similarly, if you calculate the base voltage in the section 3, you are going to get VB2 by VB3 should be in the same ratio of, what is the transformer ratio here? 66/6.6. Likewise, VB2 is how much? VB2 will be 66 by VB3, that is equals to 66 divided by 6.6, which implies your VB3 will be 6.6. Okay. So in this way, by using the voltage transformation ratio, you will calculate the base voltages. 99.99% your base voltages values will match with the transformer voltage values. 99.99%. If the examiner is sadist, then he may give you different values. Suppose instead of here, if someone tells you choose the base voltage as 60 kV in transmission line, then again the values will change. What it will become? Your base voltage here in this question, it will become 60. So from that, if you do the analysis, you're going to get your base voltage value as 10 kV. Okay, understand? Similarly, here you are going to get 6 kV. Understand? So the idea is, by using the transformation ratio, if you know the base voltage in one of the sections, you can compute the base voltage in other sections. Okay. Now I hope you have understood what is the section of power system and how to compute the base voltage of the different sections by using transformer voltage ratio. Okay. Now this last topic which I want to tell you in this context is, once you know base voltage, you can also calculate base current. So now suppose here I know my base MVA is common, that is 100 MVA, and base voltage is 1. Now base current in section 2 IB2 will become SB divided by √3 into VB. IB2 will become SB divided by √3 into VB. So 100 divided by √3 into 66. This many kiloampere will be the base current in the section 2. Likewise, you can calculate base current in other sections also. Okay. So base current in section 1 will become, the base MVA is same, SB divided by √3 into VB1. That is 100 MVA divided by √3 into base voltage in first section is 11 kV, so many kiloamperes. So identically you can calculate the can calculate the base current in the third section. So one thing you have to remember, the base MVA for the entire power system network is same, but base voltage and base current values will change. Okay. So the first step is, in the problem he will give the base MVA for the power system network, and he will also give the base voltage for one of the sections. So you have to calculate base voltages in other sections. Then depending upon the base MVA and base voltage of the element in that section, you have to calculate the per unit impedances of all the elements and connect all the per unit impedances in the form of a single line diagram. So that is how you convert the single line diagram into per unit impedance diagram. Now if you see, this is one question. This is a classic question. If you understand this question, you can do any problem in the power system per unit network. So here he has given a single line diagram. And he's asking, by choosing 100 MVA as base MVA and 132 kV as base voltage, where in the transmission line circuit 100 MVA is the common base MVA for entire power system network, and 132 kV is the base voltage in the transmission line circuit. Draw the per unit impedance diagram. Second thing, what is telling, model the load as a series per unit impedance. Here load is connected. This load, you model it as a series per unit impedance. Okay. So first is that, since you know base voltage in one of the sections, first you have to identify how many sections are there. Can anyone tell me how many sections are? Yes, different in number of sections is equals to number of voltage levels. So here it is the first section where the voltage is 11 kV, and the second section is this one where the voltage is 132 kV. This is the second section, and the third section is where voltage is 13.8 kV. Understand? So this is the third section. Okay, so we know the base voltage in which section? Section 2. So our base MVA in the problem is SB is equals to 100 MVA, which he has given, and VB is base voltage in second section is 66 kV. Okay, sorry, 132 kV. Now, what is the base voltage in first section? Let us call it as VB1. So base voltage in first section will be how much? It is in the same ratio as the, since our base voltage is matching with the transformer voltage, we can directly write our VB1 is 11 kV. Similarly, our VB3 will become, if you apply those formulas, you're going to get VB3 as 13.8 kV. Understand? So now we know our base MVA and all three base voltages. So on these new base values, we have to compute the per unit impedance of each and every element. Okay. Now first to see what is the first element, generator G1. In the first section, what is the element? Generator G1. So what is the per unit impedance of that one on these new base values? So already on the machine ratings of 100 MVA and 11 kV, they have calculated the per unit impedance, whose value is 0.15 per unit. Fortunately, our base MVA rating and our base voltage are exactly matching with the machine MVA rating and machine voltage rating. So here the new base values and old base values are exactly same. So your per unit value, new per unit value will be same as the old per unit value. So we need not calculate. So per unit impedance of generator G1, directly we can write it as how much? We can write it as J 0.15 per unit, since our base values are matching with the machine rating values. Okay. Now the second element is what? Second element is the transformer, which is 11 bar 132 kV transformer. Here he gave the per unit equivalent impedance value as 0.1 per unit. For the transformer, the per unit equivalent impedance value is 0.5 per unit. Okay. So here, if you calculate the per unit impedance either on 11 kV side or on 132 kV side, you are getting the same value, that is 0.1 per unit equivalent per unit impedance. But what is the machine rating? Machine rating is 120 MVA, but our base value is 100 MVA. So here there is a mismatch. So again we have to calculate the per unit impedance of transformer. So per unit impedance of transformer T1 is given by, so we have to use the formula Z per unit new is equals to Z per unit old into new base MVA by old base MVA into old base by a new base whole square. Okay, so now the old base MVA is 120. Here the base voltage on low voltage is 11 kV, high voltage is 132 kV. So base voltages and machine voltages are matching. So no need to bother about the voltage ratios. Just you have to take care of the MVA rating. So new base MVA rating is, this value is J0.1 into new base is 100 base MVA, machine base rating is 120 MVA. Either you take 11 kV side or 132 kV side, you are going to get this value as 1 square, because our base voltage on 11 kV side is 11 kV only. Machine transformer rating on 11 kV side, on the LT side is 11 kV. So both ratios will be 1. It will become 1 square. So what will be this value? J 0.08 per unit. Okay. So we have calculated the per unit impedance of the second element transformer. Now we have 3 transmission lines. So connected between bus bar 1 and bus bar 2 is 1 transmission line. Bus bar 1 and 3 and 2 and 3, we have 3 transmission lines. Here direct impedance is given. Directly impedance is given. So when impedance is given, to calculate the per unit value, which formula you use? Per unit impedance of transmission line between bus bar 1 and 2. So here Z per unit will become Z actual divided into S base divided by VB square. Z actual divided by Z base. So directly I am writing the formula. So this value, Z per unit value, will become how much? Z actual is 50 plus, what is the actual impedance? 50 plus J200. 50 plus J200 into the base impedance of the total system is 100 MVA. What is the base voltage of the transmission line? Base voltage of transmission line is 132 kV square. 132 kV square. Okay. So if you do this, you're going to get the value as 0.286 plus J 1.14. So many per unit. If there is any mistake, please correct. 0.286 plus J 1.14 per unit. Similarly, if you calculate per unit impedance of transmission line between 2 and 3 and 1 and 3. Why I am doing at a time? Because the both values are same. Both values 25 plus J100, 25 plus J100. So directly I am doing the at a time. Again we have to use the same formula. What is the formula? Z actual divided by Z base. So it will become 25 plus J50 into The base MVA is 100, base voltage of the transmission line is 132 kV whole square. So this value will be exactly half of the previous value. Why? Because only this base impedance value is becoming half. So you're going to get 0.143 plus J 0.57 per unit. So like this, we have calculated the per unit impedance of the transmission. Okay. So this is two values. This is one value, and this is the per unit impedance of the transformer T1. Okay. So what is left out? Now we have to calculate the per unit value of transformer T2 and G2. So again, the machine rating is different from our base MVA, even the voltages are same. So we have to calculate this one. Per unit impedance of transformer T2, per unit impedance of transformer T2 will become, again we use the same formula. I'm not writing the formula. Z per unit new is equals to Z per unit old into new base MVA by old base MVA into, since our base voltages and machine ratings are matching, so either to take HT side or LT side, the ratio will be 1 square. So this value will become J 0.04 per unit. Okay. Next, the last element is per unit impedance of generator G2. So again we use the same formula because the machine rating is different. So here it is 200 MVA machine, 13.8 kV, and the per unit value is 0.2. So even the voltage is matching, but there is a difference in the MVA rating. So you're going to get, again by using the same formula, Z per unit new is equals to Z per unit old, that is J 0.2 into our base MVA is 100 and the machine MVA rating is 200 and machine rating is 13.8, our base voltage is also 13.8 whole square. This will become J 0.1 per unit. So like this, we have calculated the per unit values of all the elements. And what is the per unit value of voltage? Per unit voltage of generator G1, that is equals to V actual voltage of the generator divided by base voltage, that is 11 kV divided by 11 kV is 1 per unit. Similarly, per unit voltage of generator G2, V actual by V base, that is 13.8 divided by 13.8, 1 per unit. By default, you can write all the per unit voltages as 1 per unit. So once you know all per unit values, you have to connect the system per unit impedances identical to single line diagram. So if you do that, what we're going to get? First we have a generator, followed by a transformer. Then there is a transmission line. There is one more transmission line. One more transmission line. And again we have one more transformer. This is 1 at an angle 0. 1 at an angle 0 because both voltages are 1 per unit. This value is J 0.1. This value we got it as J 0.04. This value we got it as 0.286 plus J 1.14. This value we got it as 0.14 plus J 0.57. 4 plus J 0.57 per unit impedance diagram of the given power system. So here you can easily compute any value. If here there is a short circuit, you can do our Thevenin's, Norton's and get the answers. Okay. So any doubt so far? Anything which I want to repeat? how to approach from a single line diagram to a per unit TRB question. So that is the first part of the question. So by choosing 100 MVA and 132 kV as base values, draw the per unit impedance diagram. Second part of the question is model the load as series per unit impedance. Model the load as a series per unit impedance. So where the load is connected at bus bar 3, and what is the value of load? 20 MVA at 0.8 power factor lag. 20 MVA at 0.8 power factor lag. Can anybody tell what is the voltage across the load? In which section the load is connected? Transmission line section. What is the voltage of transmission? What is the, so 132 kV should be the voltage across the load because it is directly connected to the bus bar 3 of the transmission line whose voltage is 132 kV, isn't it? So voltage across the load is also 132 kV. That's why he did not mention the voltage. Now, I want to calculate first Z load and then I have to calculate Z per unit load. Okay. So I don't know Z load. If I know Z load, I could have done Z load divided by Z base. So the load value has given it as S is equals to 20 MVA, 0.8 power factor. The voltage across, line to line voltage across the load is 132 kV. This is the data I know. Okay. So first you have to calculate Z load. So Z per unit load is equals to Z load, actual value of load impedance divided by base impedance. That too base impedance of the transmission line because load is connected in the transmission. Now you see, to calculate Z load, there is a formula in the first class we have discussed. ZL is given by complex power absorbed by load is given by voltage, line to line voltage across the load divided by ZL conjugate. So S load is equals to VL square by ZL conjugate. From this you can calculate ZL. So which implies ZL conjugate is equals to VL square by S load. So if you take conjugate on both sides, you are going to get ZL is equals to conjugate of any squared value is same. That is conjugate of any squared value, because any square, even if you square a complex number, the value will be real. So conjugate will not be applicable to squared numbers. So it will become VL square. This is SL, S load conjugate. So this is my ZL value. This is my ZL value. Now, what is the formula for Z base 2? Z base equals to V square divided by S base. V square divided by S base. So if I substitute in this formula both the values, Z per unit load will become VL square by S load conjugate division into, you are going to get S base divided by V base square. Okay, so this is the formula. 100% your base voltage of the system and line base voltage of the system and actual voltage will match, so both will cancel. So Z per unit load will become base MVA divided by S load conjugate. S load conjugate. Understand? So S load value, first you have to calculate. Since you know this value, S load will become, real part is 20 into 0.8, 16 megawatt. Reactive part is, since power factor is lag, 20 into 0.6, that is J12. This many MVA, that is S load. So S load conjugate will become 16 minus J12 So if you substitute in this formula, you are going to get base MVA for the problem is 100 divided by S load conjugate is 16 minus J12. If you simplify this value, you are going to get how much? So you have to take complex conjugate. So it will become 625. So you are going to get this value if you simplify 4 plus J3 per unit. 4 plus J3 per unit. That is my answer. So where I have to connect this load? This load is connected at bus bar 3. This value is 4 plus J3. 4 plus J3. This is how you simplify the load if you calculate the load impedance of the per unit impedance of the load. You simply have to remember this SBS divided by S load conjugate. Then you can calculate the per unit impedance of load. So that we have calculated this value as 4 plus J3. 4 plus J3 per unit. 4 plus J3 per unit. Okay. So this is one of the typical questions on conversion. If you understand this question, you can do any conversion. Okay. Now I am giving a simple question. Carefully read. Here there is no transformer. Your life is very easy. He has given all the data. Try to find out what is the positive sequence. What is the per unit impedance diagram for this given system with given data. 4 options are also given. Okay, I'll give 2 minutes. Try to solve this problem. So here he has given the percentage reactance. So per unit reactance is percentage reactance divided by 100. So the Xg1 per unit reactance is 0.25 per unit, and Xg2 per unit value is 0.1 per unit on its own base value. The transmission line reactance value is 0.225 ohm per kilometer. So for 10 kilometer, this value will become how much? For 10 kilometer, this value will become 2.25 ohms, and this value also will become 2.25 ohms. So you know the actual values here, you know the per unit values of generator G1 and G2. Now you have to calculate the positive sequence diagram. So don't worry about the positive sequence term. Positive sequence means power system is balanced. Positive sequence means when the power system is balanced. Okay, so far we have not entered into unbalanced analysis. So by default, all the networks are positive sequence networks. Now, find out the per unit values on a 100 MVA base. There is a print mistake. It is a 100 MVA base MVA, 100 MVA common base. Okay, he did not mention the voltage base. Why? Because the entire network is at the same voltage. Here also voltage is 15 kV, generator voltage is also 15 kV, transmission line voltage is also 15 kV, and generator G2 voltage is also 15 kV. So our base MVA is 100 MVA. The base voltage is 15 kV. Now we have to calculate the positive sequence network or per unit impedance diagram for the given power system network. Okay. Now, per unit impedance of generator G1. I'm directly writing per unit impedance of generator G1. G1. It will be how much? Already we know the per unit value. The per unit value of this one on its own rating is 0.25, but the machine MVA rating is 250 MVA. Voltage is same, no issue. So our new MVA rating is 100. So you're going to get 0.25 multiplied by new base MVA is 100. Old base MVA, that is machine MVA, is 250. Both base voltages are 15 square. So you're going to get J 0.1 per unit. Similarly, per unit impedance of generator G2 will become, here also the value is J0.1. Now here machine MVA rating and our base MVA rating both are matching, so we need not calculate, it will remain same. That is J0.1 per unit. Per unit impedance of transmission line. Here there are two sections, both sections actual impedance is J2.25 ohm. Actual impedance multiplied by base impedance, that is given by S base divided by VB square. So 2.25 multiplied by base MVA is 100 divided by base voltage is 15 square. So this value will become how much? This value will become J1 per unit. So other transmission line value will also be same. Why? Because both are having same impedance. So if you connect all the four values, you are going to get, this is your per unit impedance diagram, where the values are 1 at an angle 0. All voltages by default you can write 1 at an angle 0. J0.1, J1, J1, J0.1. So this is the per unit impedance diagram. Which is the right option? Option A is the right option. Option A is the right option. Okay. So this is the correct option. You can see J0.1, 0.1, J1, J1. So all voltages he did not mention. These values will be 1 at an angle 0 and 1 at an angle 0. So this is the per unit impedance diagram for the given system. Okay. So with this per unit